Welcome to our cosmic journey through the life cycle of stars. Today we'll explore how stars are born, live, and ultimately meet their spectacular ends. From the unimaginable vastness of interstellar space, where gravity sculpts clouds of gas and dust into celestial fireballs, to the dramatic deaths that echo across the cosmos, we'll witness the awe-inspiring power of these stellar giants. But beware, for within this cosmic furnace lies a secret, an unexpected twist that defies all we know. Join me and let's uncover the mysteries that could change our understanding of the universe forever. Our story begins within a nebula, a vast cloud of gas and dust scattered across the cosmos. These cosmic clouds, often remnants of past stellar explosions, become the birthplace of new generations of stars. Picture, if you will, these enormous cold and dark clouds, composed primarily of hydrogen and helium, the most abundant elements in the universe. Over eons, gravity, that invisible force that shapes the cosmos, draws these particles together. As the cloud collapses under its own weight, it fragments into smaller, denser clumps. Within these clumps, gravity continues its relentless work, pulling the gas and dust inward, increasing the density and temperature at the core. This protostar, a stellar embryo, grows hotter and brighter, radiating energy into the surrounding space. Millions of years pass, and the core of this collapsing cloud reaches a critical temperature, a scorching 10 million Kelvin. At this moment, a star ignites. Nuclear fusion, the engine of stars, begins. Hydrogen atoms, under immense pressure and heat, fuse together, forming helium and releasing a tremendous amount of energy. This energy, in the form of light and heat, pushes outward, counteracting the inward pull of gravity. A star is born. Now blazing with light and heat, our newborn star enters what we call the main sequence, a period of stellar stability where it will spend the majority of its life. This phase is marked by a delicate balance, a cosmic dance of forces that keeps the star shining steadily. Think of it as the star's adulthood, a time of equilibrium where the outward pressure from nuclear fusion perfectly balances the inward crush of gravity. This equilibrium is crucial, as it ensures the star remains stable and continues to emit light and heat. But this stability doesn't mean all stars are created equal. Stars come in a variety of sizes and masses, each with its own unique characteristics and life cycles. The lifespan of a star, the time it spends in this main sequence, is intricately linked to its mass. The more massive a star, the shorter its life, as it burns through its fuel more quickly. Smaller stars, like red dwarfs, are incredibly efficient, slowly sipping their hydrogen fuel over billions, even trillions of years. These stars are the slow burners of the cosmos, conserving their energy and shining dimly but steadily. These cosmic elders will long outlive our own sun. They are the ancient keepers of the galaxy, witnessing the birth and death of countless other stars. Larger, more massive stars, on the other hand, are like celestial rock stars. They live fast and die young. Their brilliance is short-lived, but they leave a lasting impact on the universe. Their immense gravity creates intense pressure and heat in their cores, causing them to burn through their hydrogen fuel at a prodigious rate. This rapid consumption leads to a shorter, more intense life. These stellar behemoths may only shine brightly for a few million years before their spectacular demise. Their end is often marked by dramatic events like supernovae, which can outshine entire galaxies for a brief period. Our own sun, a yellow dwarf star, falls somewhere in between, destined for a lifespan of about 10 billion years, of which we've experienced roughly half. This middle path allows for a stable, long-lasting star that provides the perfect conditions for life to flourish on nearby planets. But even stars, those seemingly eternal beacons in the night sky, are not immune to the passage of time. They are born, they live, and eventually they die, undergoing a series of dramatic transformations that are as awe-inspiring as they are inevitable. As a star exhausts the hydrogen fuel in its core, its internal balance between gravity and nuclear fusion begins to falter. This delicate equilibrium, which has kept the star stable for millions or even billions of years, starts to break down. For low to medium mass stars like our Sun, this marks the beginning of a dramatic transformation. These stars, which have spent the majority of their lives in a relatively stable state, now enter a phase of significant change. With hydrogen in the core depleted, the star begins to fuse helium, creating heavier elements like carbon and oxygen. This process, known as helium burning, generates even more energy and leads to further changes in the star's structure. This new phase of fusion releases even more energy, causing the star's outer layers to expand outward, ballooning it into a red giant. The star's outer envelope swells dramatically and its surface cools, giving it a reddish hue. Imagine our Sun, swollen to such an enormous size that it engulfs the orbits of Mercury, Venus, and even Earth. This immense expansion is a stark reminder of the dynamic and ever-changing nature of the cosmos. This red giant phase is a cosmic prelude to a star's final act. It is a period of both grandeur and instability, as the star prepares for its ultimate fate. The outer layers of the star, now loosely bound by gravity, are gradually ejected into space, forming a breathtaking cosmic spectacle, a planetary nebula. These ejected layers create intricate and beautiful patterns as they drift away from the dying star. These glowing shells of gas and dust, illuminated by the dying star at their center, are some of the most beautiful and awe-inspiring sights in the cosmos. They serve as a testament to the star's life and its final, spectacular transformation. As the planetary nebula fades, all that remains is the star's core, a dense, hot ember known as a white dwarf. This remnant is incredibly dense, with a mass comparable to the Sun's but packed into a volume similar to Earth's. This stellar remnant, no larger than Earth, will slowly cool over billions of years, eventually fading into a cold, dark black dwarf. This final stage marks the end of the star's long and fascinating journey through the cosmos. But for massive stars, those cosmic heavyweights, death is anything but quiet. These colossal entities, often tens or even hundreds of times the mass of our Sun, live fast and die young in cosmic terms. Their lifespans, though millions of years, are mere blinks in the grand timeline of the universe. These stellar giants, having burned through their fuel at a breakneck pace, face a far more dramatic and violent end. Unlike smaller stars, which can burn steadily for billions of years, massive stars consume their nuclear fuel rapidly, leading to a series of increasingly desperate attempts to stave off collapse. As they exhaust the helium in their cores, these stars begin to fuse heavier and heavier elements, creating a layered structure like a cosmic onion. Carbon fuses into neon, and the process continues, with each successive layer representing a different stage of nuclear fusion. This intricate dance of elements is a testament to the star's struggle to maintain equilibrium. Neon into oxygen, and the cycle goes on, each fusion stage shorter than the last as the star races towards its inevitable fate, and so on until the core is primarily composed of iron. Iron, however, is the end of the line for stellar fusion. Unlike lighter elements, fusing iron doesn't release energy, it consumes it. Iron, however, is the end of the line for stellar fusion. This marks the beginning of the end for the star. With no more energy being produced to counteract the force of gravity, the core becomes unstable. Fusing iron requires more energy than it produces, and with the core no longer able to support itself against gravity, the star's fate is sealed. The core collapses under its own immense weight, leading to a dramatic and catastrophic event. The core collapses in on itself in a fraction of a second, triggering a shockwave that rips through the star, tearing it apart in a cataclysmic explosion, a supernova. This explosion is one of the most energetic events in the universe, capable of outshining entire galaxies. For a brief, shining moment, the supernova outshines its entire galaxy, releasing more energy in a few seconds than our Sun will emit in its entire lifetime. The brilliance of a supernova is a spectacular sight, visible across vast distances in space. These explosions are the universe's grand recycling plants, scattering the heavy elements forged in the star's core across the cosmos. These elements, such as gold, silver, and uranium, are the building blocks of planets, moons, and even life itself. The remnants of this cosmic explosion depend on the mass of the core. The aftermath of a supernova can lead to the formation of some of the most exotic objects in the universe. If the core is between 1.4 and 3 times the mass of our Sun, it collapses into an incredibly dense object called a neutron star. These stars are the remnants of the supernova explosion, incredibly dense and compact. These bizarre objects just a few miles across are so dense that a teaspoon of neutron star material would weigh billions of tons on Earth. The density and gravity of neutron stars are so extreme that they challenge our understanding of physics. And if the core's mass exceeds 3 times that of our Sun, gravity's pull becomes insurmountable. The core collapses endlessly, forming a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. The formation of a black hole marks the ultimate end for a massive star. These enigmatic objects are the final stage in the life cycle of the most massive stars, leaving behind a legacy that continues to intrigue and mystify scientists and astronomers alike. And that's the incredible life cycle of stars. From their fiery births to their dramatic deaths, stars play a crucial role in the universe, continuously enriching it with the elements necessary for life. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in the hearts of stars that lived and died long ago. As we gaze up at the night sky, let us remember that we are not just observers of this cosmic drama, but active participants. We are, after all, stardust, connected to the universe through this grand cycle of stellar life and death. Thanks for joining us on this cosmic journey.